before I start doing the problems from the end of the unit, I'm going to do like a brief, like 10-minute lecture over a couple concepts that relate to what we have been doing. And I'm just going to do it because I'd rather get the lecture out of the way now. Yeah, certainty in an uncertain world. It is an uncertain world, eager young minds. How do we quantify that? How can we be certain of it? How do we express this? That's right. Odette can never be sure with any certainty which reflection she will see of herself in the mirror. Oh, yeah. Deep, yeah. The words, accuracy and precision. Yes. Yeah, okay, good. What are they? What is accuracy?
Okay, well, now I can't. But one of them means that or like you keep like every time you try something. And the other that your outcome, but
you're so close. You're right there. You're saying things. You haven't said anything that's incorrect yet.
I can't remember. But I learned.
You are learning a lot. You're close. You're very close. Yeah.
Yeah, that's
who talked about that? Was it who? Is that the science person? Yeah. Cool. Yeah, I haven't had a chance to take a class from her yet. Was it this picture that she showed?
Yeah.
Yeah. So accuracy is just when you say how accurate are you, that means how correct is it? When you when you have a value or when you have a statement, how close to the truth is it? If it's possible to know a true value, then you can know the accuracy. If it's impossible to know a true value of something, then you won't be able to know the accuracy. Precision, having a highly precise instrument, is one that is very reproducible. It's going to give you an outcome that's the same every time. All right? The same every time. So, for example, we're shooting arrows. And every time I shoot, I'm hitting right here. This is very precise. I'm hitting the same spot. But I'm not very accurate because I want to be hitting here. This is the truest spot that I could be hitting. And I'm not doing that. I'm hitting over here. So this is high precision, low accuracy. This is low accuracy. They're all spread out. Oh, low precision, thank you. But it's actually high accuracy because these two values here and here average out to be in the middle. These two values average out to be there. This one is in the middle, and there's just this one outlier that's not really balanced by it. All right? So that's pretty accurate, but not very precise. This is just crap. And that is both precise and accurate. All right? So let's see. Oops, going backwards. Yeah, we got what they meant. So precision is how reproducible is something, and accuracy is how close to the true value. So they're not the same thing, but they are related, right? They are related. And the answer, can they be numerically quantified? Yes. And we're going to very lightly scratch the surface. Very lightly, because these two concepts can be applied in a surprisingly broad range of applications. Yeah.
Sorry.
Miles, yes.
So why would
I didn't say precision was better. I didn't say precision. Sometimes, depends on what you're doing. Sometimes precision is important. Accuracy is important. Okay, let's see it.
I am not. Good.
Yeah. That's really good. Wait. Well, hold on a second. We got to get that. I'm doing it right now.
No.
What have you people done?
Thing 1. Oh, wait. Yeah. We should get thing 1 and thing 2. I am not precise because I am not reproducible. Thing 2. Accurate. Should we say that's accurate? Make it a sentence. She snorted. Oh yeah.
Thing 2 is 1.
Thing 1, thing 2. That, yeah. There we go. I kind of. Is that right? You would not like to live my life then.
Most of America is terrible at making this.
Are you gonna get a picture?
I agree with that. Get ones from the Cat in the Hat movie live. No. The movie ones.
The movie ones. These two.
Those ones right there. Yes.
That's
Yeah, we
terrifying.
look exactly like that.
Yeah.
All right.
No.
Oh yeah.
Which one? Which one?
The one you can take separate. The one.
Those little babies look pretty weird.
Oh my god, that one. That one. The one.
Yes.
Not that one. No.
No, that's a good one too, though.
That's a good one too, but the one up. The one where like both of their faces are super close. They're wearing like blue.
Point to it. Which one? This? Oh, this one?
Yeah. God, that's terrifying.
God.
That is so scary. That looks like some type of thing Mr. Shea would do for Halloween. For real.
All right. I'll make that look better later.
Nice.
Okay. Yep. That was good. Thank you.
Thank you.
Right. Okay.
Use that in the future.
So, as we see, it can be applied to theater. It can be applied in all sorts of ways to archery, but it can also be applied to data, right? And specifically to the data that we collected. Here is an actual sine, right? That's what the sine function looks like. This is some hypothetical your data. This is your data that you collected. It's not. I don't know. These are circles that I put on the slide. Well, I don't know. I think it's reasonable. And then I just reflected it and translated it, which is the same thing you guys did last class period, right? We already did this so that it extends throughout quadrants 1 through 4, where this represents quadrant 1, this represents quadrant 2, this represents quadrant 3, this represents quadrant 4. And keeping in mind what I'm mapping here is the sine value, the value of the trig function versus theta. So this is sine theta versus theta. This is not x and y. All right. When you think about the accuracy of something, the accuracy is comparing your data point to what the actual sine value is. We know what the sine value is. We know what the actual sine function should return. And we're comparing it to your experimentally measured thing. So the accuracy is a measure of how far away from that sine value you are. The precision is comparing how clustered the ensemble is to that function, right? So let's see if I can. I think I have some examples. So low accuracy, high precision. All right? It's not actually very close to the sign value, but I was pretty precise in reproducing, a number that was, it's pretty consistently or systematically inaccurate, meaning it was precise. Does that make sense? Here is high accuracy, but low precision. Like it's kind of far. They're kind of systematically far away from the actual value, but it averages out so that it's actually pretty accurate, taken as an ensemble. Here's high accuracy, high precision, and I didn't do the total crap. So, unsurprisingly, there are ways of quantifying this. So, for precision, that method is what's called the standard deviation. And the spreadsheet will calculate standard deviation. We'll do it for you. All right. There's just like there's the sum if function, all the other little functions. There's the SDEV function where the spreadsheet will do it for you. But I'm going to show you what we're gonna look inside of that just a little bit so you can see what it looks like, and so you can begin to see some of the mathematical expression. Like when you look at that, you don't get scared. That this is an understandable thing. So the standard deviation equals the square root of this expression, and the expression is simply the difference between x sub I, which is the sample variance for I, and I'll go through what variance is. The sample variance is just how much that point varies from the actual term, right? So it's the difference between the variance for that point and the mean, all right? The mean of all of the variances. So if you take all of these variances, find out what the average is, and then you take the difference between a sample variance for item I, whichever item I is, and then you square that and sum that up from 1 to n. And in this case, n is the last one. So n here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times 4, 44. N would be 44. All right? So you take those 44 numbers, which is the difference between this value for each of these and the average variance squared, and simply divide that by 43. That is the definition of standard deviation. We're not going to... What's that? Yeah, 43, right? 44 minus 1. So that is the standard deviation. I'm not going to go through the derivation of that or why it is considered to be a reasonable representation of the precision, but you can begin to think about it though, right? Like, so we're looking at how, for each of these, how far one of these things is away from the the mean of the difference. So if this cluster of values was widely spread, right? But then you took the average of the variance, you'd have some mean value, and say it was highly accurate but very imprecise. That mean would be pretty small, right? Because this value is going to be different than if it were down here. That mean will be, the values could be very accurate, but if they are imprecise, that variance will be kind of high. So this value will get large. And so the square of that is going to lead to the square root of that is going to lead to a large standard deviation. And standard deviation is just how much are these points deviating from one another is really from the clustering. How tight is that clustering? The smaller the standard deviation, the more precise. And the larger the standard deviation, the less precise. And then accuracy is very closely related. And I don't want to get too deeply into this, but I'm just giving you enough of this so that we can apply it and be able to say something about whether our data set is accurate and or precise. All right. So there's a lot of more math and theory behind this that I'm not going to. But the thing that we use to determine accuracy is called the standard error. The standard error. It is related to all this, where the standard error is essentially the standard deviation, which here I'm representing it S, divided by the square root of n. All right? So it's the standard deviation divided by the square root of n. And that is a term that enables us to have some sense of how close it is to the actual true value. The assumption that this is not absolutely true. So you can see here that there are these squiggle lines because the assumption that's based on is that if n was infinity, that you would have an infinite number of values, that you would have an absolutely accurate representation. So it's assuming that all of your sampling, if you could sample infinite number of times, that the average would be the exact true value. That's an assumption, all right? That may not be correct, but it often is. So that's one of the assumptions based upon it. It makes the math easier. It makes the math easier. If it is true that if you were to sample infinitely, that you would get an absolutely perfectly accurate mean, then this expression works. If that is not true, then it falls apart and there's a little bit more complicated. So all I really want you to know is that standard error of the mean gives us information on accuracy, and standard deviation gives us information about proof. That's the takeaway. I gave you just enough math to seem like it's not completely magic, but it's still fun. Yeah. So I think that is the last thing I said is you can also look at replicate data. So the green might represent Slytherin and Ravenclaw, or I don't remember what the groupings were, and then blue was Hufflepuff and Gryffindor. You can add them together, right? And that would increase your n, right? That would increase your n, and may increase your accuracy, right? Because by increasing n, you're decreasing the value of the standard error of the mean, because the n is in the denominator, so it's making that standard error smaller. Right? The more you sample, the smaller your standard error is. The smaller the standard error, the more accurate. How many people did I lose? Some, few, kind of. All right, is anybody completely lost? Okay. Yeah. What parts of this? So let's go to the takeaway before we get into all the stuff on the concept that standard error of the mean is accuracy and standard deviation is precision. That is straightforward. And as the number of samples goes up, you would imagine that you're going to hone in on a more accurate mean, right? So it's like imagine if you had a tape measure, you were going to measure this thing. You take one measure, and then you write it down, and you take another measure, and you write it down, and you take a third. The 3 measurements should be more accurate than the 1. And if you do it a million times, the mean is going to be very close. If you do it a billion zillion times, then you're going to be honing in on the actual. Yeah. The mean is So imagine, yeah, mean is an average. A mean is just, so the mathematical expression for a mean is I to n of I divided by n. That's the math. It's just like taking, so you have three numbers, 3, 4, and 5, and this equals I equals 1. So this is item 1. I equals 2. I equals 3 here, and n equals 3. You're just going to add up. This is a summation. Is anybody not familiar with the summation symbology? Okay, yeah. This sigma, that's the sigma, the Greek letter sigma, and it just means it stands for sum. So I'm going to sum some element up, and in this example, I'm going to sum some elements, some element I, from I, whatever some integer is, up to n, the number of items that I'm sampling. So if these are my three things that I'm adding up, the values 3, 4, and 5, I starts at 1, and then 2, and then 3. So I'm going to add up 3 items up to 3 is my n. There's 3 of them, and it just says I, right? So I could do the sum of I to n of 3 times I. And that would just be, and if this was my data set, it would be 9 plus 12 plus 15, right? That would be this sum. So it's just how to sum things up. And this, yeah, it should have been part of pre-calculus class, like a proper pre-calculus. But that's the doorway into calculus, like learning how to do sums. It's like super tedious, and then you learn to do calculus. Oh shit, but we're not. But that's the summation term. A mean is just the average. It would be adding 3 plus 4 plus 5. That's 12, right? And then dividing by 3. The average here is 4. You can see that. So a mean, that's just the symbol. That's the symbology. Everything. Average. The word average itself is not an explicit mobile, but mean is saying something very specific. Huh? Average is not, the word average is often taken as a synonym for mean, but in mathematical language, it's not. The word average is sort of a loosely defined term, whereas mean is saying something exact, right? Yeah. Mean has a very specific definition, and this is the definition, right? Adding up, you basically just add up the elements in your set and divide by the number. That gives you the mean. Or often, lazily, people call it the average, but there are different ways of types of average. Yeah. Yeah, that's a mean. That's, and I know it is confusing because what language did I use? Well, yeah. This here, this term, it says average, but this actually means mean.
Ooh.
The bar that's over there. Yeah, pardon me. Yeah, when you have a some number or a symbol with that bar over the top, it means mean. Unless you see something like 4.3 like that, then the bar means that it's okay. It's math. Yeah, math. Yeah, but the basic idea is that there is going to be like an average distance of some point. Say we're like sampling right at this angle, whatever angle we were at here. That was I don't know, like 140 or and you got one data point here, one's here, one's here, one's there, one's there, one's there, right? All these data points. Did I might not have, yeah, I deleted it. I had this one slide that I made that explained it a little bit better, but it was like kind of complicated. If you could imagine taking this cross section right through here of all these samples that you took, if you took 1,000,000 of them, and then you looked at it, it would look at, if this was the middle value, it would be something like that, right? Of like if you were to stack all these values you had up, it would be like this bump that would be coming out of the board and then back into the board. And that perfect average would be right at the true value, okay? So as you head to infinite number of bumps under that curve, the more this mean approaches and equals the actual value. Does that make sense? And as that happens, your error goes down. As n goes up, the error goes down. The more times you sample, there's that assumption. The more times you sample, the more accurate your sampling gets. Does that make sense? So that's the basic. That's the basic. Yeah. So like, it takes a while to learn how to look at that. Some sigma notation is what it's called. But we're not going to work on that yet. All right.